into the nice sunshine. So I'm going to talk about model uncertainty, which I guess is what this whole thing is supposed to be about. My name's Tony O'Hagan, and I'm retired. So what am I doing here? I don't know. We'll move on. The outline of the talk. So we're going to begin with the introduction, principal sources of uncertainty in model predictions, and the first three consequences of ignoring them, and then the calibration, physical and tuning parameters, etc., etc. You can read it. I don't need to read it out to you, but we're going to go through this whole process, and we're going to end up with 5 consequences for you to take home as your take-home messages from the talk. Okay, so introduction. So you've got yourself a model, and already the real cardiac experts in this audience will realize I'm not one of you, because I put up such a naff picture here, okay? But that's what I found on the internet, and it looks pretty. But I'm not going to talk about cardiac models. I'm going to talk about models generically. So I'm going to talk about hydrological models for rainwater runoff in a catchment. I'm going to talk about models for deep deposition of nuclear waste, climate models, molecular models, models of physical engineering structures. Any of those models, whatever I'm talking about is generic for all those kinds of models. Models that are mechanistic, that encapsulate the science that we believe we know about in relation to a particular problem. So you want to use this model to predict something, of course, or to help you to make decisions or something like that. So you've got the model, we'll call it the simulator. It's got inputs and it's got outputs, and you need to supply the input parameters. That's the first problem, isn't it? So, well, you go and put in your best guesses, or the nominal values, or the values that the guy next door has put in, or the values that are always put in for models of this kind, and out pop your predictions. Job done. Hooray. But unfortunately, the recipient of this model prediction says, how good is it? Well, it's as good as I can make it. Best possible model, that's it. How good is that? Well, it's really good because, you know, I'm good at this, right? Okay? But it's not perfect. Surely it's not perfect. It won't exactly equal the true value, will it? Right? Well, not exactly. I mean, you know, I estimated the inputs, but they're good estimates, aren't they? So how far from the true value is it likely to be? I don't know. Didn't actually answer that question. And then the guy's not interested anymore. Okay? So ignoring uncertainty, your first consequence is, if you don't acknowledge any uncertainty in the model predictions, if you don't try and quantify it, why would anybody take you seriously? Model predictions are useless without a quantification of the uncertainty. You have no idea how good it is. So why would you use it? Okay? So far so good. I'm sure you all have bought into this already because you're here, right? So you decide to allow for your input uncertainties. Okay? First step, you put probability distributions on all those inputs. But how do you put the probability distributions on all those inputs? If I read through all the UQ literature, there is almost nothing telling me how to put probability distributions on the inputs. It tells me what to do with them when I've got them. So, well, you analyze some data perhaps, or you use the quoted error bounds for the numbers that you're putting in. Or you could actually go and seriously elicit expert knowledge and judgments about these things because you want to do it as well as possible. And even if you're analyzing data, and even if you're using quoted error bounds, there's still judgment involved. You're still having to decide, do I trust these data rather than something else? What sort of distribution do I put to go with those error bounds? This is all judgment, and it should be expert judgment. It should be carefully thought through judgment, because those probability distributions matter. They're what drive the uncertainty in the output, or at least part of it. So do it properly, and eliciting expert knowledge is one of the things I take very seriously and do quite a lot of work on. But then you propagate the uncertainty through the model. This is what UQ is really all about most of the time, propagating the uncertainty. How do you do that? Well, Monte Carlo, of course. It's nice and quick and easy. Well, depending how quick your model is, of course. Or you build an emulator, good things emulators. Or you use polynomial chaos or one of those other kinds of surrogate model building tools. And then you add in the propagation uncertainty. Now, we've just done that, haven't we? Propagating uncertainty. No, this is something else. This is what is the uncertainty in the process you've used for propagation, because that's not perfect, that's not precise. And you can only do that if you've used a statistical method like Monte Carlo or an emulator. You cannot do it with principal components, not principal components, what do you call them? Polynomial chaos, one of those little PC things. Okay. You can't do it with just something which is a model fitting tool, because it doesn't quantify uncertainty in the quality of the fit. If you use polynomial chaos, you've truncated the series at some point. You have no measure for how accurate it is as a result of doing that. So, there are two sources of uncertainty we've now got to think about. There's the uncertainty on the inputs, but then there's also the uncertainty on the propagation. Monte Carlo will quantify the uncertainty for you, so will an emulator. So you should include that as well, because otherwise you're underestimating the uncertainty in the model predictions. And underestimating it is almost worse than not putting any uncertainty in at all. Because you're kidding yourself, or you're kidding the recipient that this is the extent of the uncertainty. No, it isn't. There's more. And there's even more. There's one more important source of uncertainty to take account of, which is that all models are wrong. So there's another uncertain component there, which I call model discrepancy. Does this work? No. Model discrepancy. There you go. Between your model outputs and reality, there is this further thing, which is what is the difference between the model prediction, even using somehow the right or the best values for the inputs, difference between that and reality is not zero. More models are wrong. And it's also very uncertain. Most people have a very good idea about how close their model is getting to reality. You can only do it, you can only get some handle on it by looking at reality and comparing it with your model outputs. And that is a whole bunch of complicated stuff which we'll come to. So, third consequence, not accounting for the additional uncertainty due to the model discrepancy means you are again underestimating, understating the uncertainty in your model predictions, often by quite a large amount. And it's not enough to say, well, I've accounted for this amount of uncertainty, I know there's some more, I have no idea how big that is, because you're back to the state of the recipient has no idea how to treat your model predictions. If you cannot say how good they are, they don't know how much to trust it, what to do with it. So this talk is going to focus on that last component of uncertainty, the model discrepancy. I'm going to tell you what the consequences of ignoring it are, and actually consequences of not ignoring it. So let's have some notation. The simulator I'm going to describe by the letter eta. Eta has two sorts of arguments. This is typical of all kinds of models and simulators. It has what I call control inputs, the things which describe the particular instance that you want to run the simulator for in this case, the particular local conditions or whatever it is. And then there's these uncertain parameters, the parameters which are built into the model and which influence all the predictions it makes. Then we're going to have reality, which is zeta, which is going to be eta plus delta. Delta is the model discrepancy. And notice the model discrepancy is a function only of the control inputs. We're assuming when we talk about the model discrepancy that somehow the right or the best values of theta are in there. Reality doesn't know what theta is either. Theta is just a construct in your model. So the three sources of uncertainty in the order I've introduced them are parametric uncertainty, uncertainty about theta. Then the propagation uncertainty or code uncertainty, uncertainty about eta. The fact that you cannot run eta, cannot run this model at every possible set of inputs. So when you propagate the uncertainty, you have to somehow take account of the fact that you haven't done it at all possible inputs. For instance, you've done Monte Carlo, you've run it as a sample of inputs only. And finally, the third thing is model discrepancy delta. Those are the three principal sources of uncertainty in your model outputs. And if you don't include something about them all, if you don't treat them all seriously, then nobody should treat your model seriously. So, I'm going to talk about calibration particularly. The reason for this is that, as I said, in order to get any sort of a handle on the model discrepancy, you need to do something about observing reality to check. So when you observe the reality, the two principal things you can do with that are validating your model. So are the observations consistent with the predictions and the stated uncertainty? Now when people talk about model validation, they don't usually mean that. Model validation in this sort of verification and validation paradigm is I compare my model predictions with no mention of model uncertainty, model discrepancy rather. I compare my model predictions with reality and I say, is that good enough? Is that close enough? No, that's too wishy-washy, okay? What I want to say is, I'm making a statement with this model, which is, here's an estimate, a prediction, and here's a statement of uncertainty. And I can validate that. Remember, valid sounds to me like something that's really quite definite, quite absolute. Not a wishy-washy, that's good enough thing, okay? So I can say whether my predictions are valid as long as I put the uncertainty statement on, and I can validate that. Are my predictions, including the uncertainties, and also including the measurement uncertainty, of course, in the observations, is all that consistent with what I see? I'm not going to say any more about that, but that's actually a very important topic, and I'm quite passionate about validating it this way rather than the usual sort of, is this good enough for what I want to do? So, calibration. Calibration is the other thing. You learn about the parameters and you learn about the model discrepancy. You learn about everything that you're uncertain about in principle, and it helps you to reduce that uncertainty in principle. So if you don't include the discrepancy, it looks like this. You have a simulator and you have observations. So I'm going to call the observation Z, and the simulator plus observation error. And this is just a nonlinear regression model to a statistician. Calibration problem is just one of statistical inference about theta. And we can do that straightforward. I'll be using Bayesian methods, of course. Of course. We need a prior distribution for theta. Well, that's what you started with, is your statement of your uncertainty about the parameters before you put in before you observe the reality. But they often, in this sort of situation, assume a non-informative prior for that, which I don't understand. I mean, the whole point is to improve your understanding. So you start from somewhere and you get better. You don't start from nowhere. But anyway, then you produce a posterior distribution. That is the result of having learnt about theta. And then you can propagate that through the model, and you can get your new prediction uncertainty. Parametric uncertainty will have been reduced. You won't reduce the propagation uncertainty, but that's fine. But you should be putting your model discrepancy in, of course. And then you get a slightly more complicated model, because you're not observing model plus observation error. You're observing reality with observation error. So I'm going to write Z is reality zeta plus observation error, epsilon. So it's eta plus theta plus epsilon. Lots of lovely Greek in there, okay? Inference about theta is now clearly more complex. It's no longer just a nonlinear regression problem. And one point about this is that if you think of delta plus epsilon as your error on your model, comparing the model prediction with reality, now it's going to be correlated errors, which is very important. So how important is it to put model discrepancy in? Well, it does depend on what you want to do, and in particular on the nature of theta. So calibration and the nature of parameters. Parameters can be physical, have real physical meaning, or they could be just for tuning. So we adjust the tuning parameters just to fit the model into the observations as closely as we can. We're not really interested in the values of those parameters. Sometimes the value of the parameter, the tuning parameter that you get, gives you some indication of what you've not got right in your model, but that's a side benefit, if you like. We're not really interested in the values of the tuning parameters. We just want to get them to represent the reality fairly well. But the physical parameters are different. They're important. Their true values have some meaning within the science that you're talking about. So you could be calibrating primarily to learn about those parameters. That could be the way that your science is going to progress. Learning about those physical parameter values is often an important feature of designing models and running them against reality. You could be using this calibration process just to interpolate, so to be able to predict what's going to happen at other values which you haven't yet observed, but which are within the range of the data and the scope of the problem that you've been working on in this particular case. But extrapolation is another important issue. A lot of the time we build models, we can observe them in certain situations, but we can't observe them in the places where we really want to make the predictions. Very often that's the purpose of building the model, the fact that you can't observe in certain situations. So extrapolation is an important process, and that's where physical parameters are terribly important. Tuning parameters can be all over the place, and they don't help you to predict at all, because they tend not to stay constant. The point about the physical parameters is they're supposed to have some meaning which is consistent, which works through all possible sets of your control parameters, all possible uses of this model. They're the only way that your model can usefully be calibrated to help you to predict and outside the range you've got data, this extrapolation problem. So the physical parameters are the key to your model working in an extrapolation sense. So I'm going to give you two very, very trivial models. They're both models with one input and one output. So that's pretty trivial already, but they're really, really very simple. The point is just to demonstrate some principles here. So, and also, by the way, for all the applied mathematicians in the audience who know about these sorts of mechanical processes, I probably got the physics of whatever it is all wrong as well. That doesn't matter. The point is that it's a simple model. So a machine produces an amount of work which depends on the amount of effort you put into it. So your input is X, your output is Y, and we've got an ideal machine here. Our model says Y is beta times X, where beta is somehow the rate of conversion of the input effort to output work. But it's a physical parameter. It's a physical parameter that in my model is going to have a true value of 0.65. I'm going to denote that by beta star just to be sure what we're talking about. So here's the graph of the data and the correct value of beta 0.65 straight line model prediction. And of course the points are lying below that line because, well, there's some losses due to friction or something like that. And the true model is this zeta here. It's 0.6x times 1 plus 0.05x to the minus 1. My observations, by the way, are made with tiny, tiny errors. Those circles don't exactly fit on the line, but I'm making tiny errors to emphasize the point. Now, if you actually plotted that, of course you would see that you haven't quite got the model right, but let's just proceed for the moment saying you haven't spotted that. So we've got all these observations which are spread over the range from just above 0 to 4. Now this another example before we proceed any further. My second example, an object is placed in a hot medium. It heats up and then the whole setup, the object and the medium cool down. So it's going to get hot and then it's going to get cold again. My simulator looks like that. Reality looks a little bit different, but they both do the same thing. They go up and then they go down. The parameters are physical. Well, at least θ1 is. θ1 definitely, its initial heating rate is a property of the object, how much it could take up that heat. Oh, obviously it depends on the temperature of the medium. θ2 controls the cooling, it's a property of the medium and the experimental setup and so on. We're interested in these parameters, and we're also interested in the time at which the temperature reaches a maximum and what the maximum temperature is at that point. So we'll be interested in 4 things in this particular model. So, meaning of the parameters. What's the relationship between the parameters and reality? Because the parameters themselves don't appear in the model for reality. Reality is zeta of x, not x and theta. Now, in the simple machine model, beta is the gradient at the origin. Okay, it's the theoretical efficiency. It's only achievable at low inputs before you start getting these losses due to friction, etc. So it's actually well defined for reality. It is a physical thing. It will be 0.65 in this particular example. In the hot and cold example, θ1 is again the gradient at the origin, and that's again well defined. θ2 is a little bit more difficult because in reality the cooling isn't exponential like our model says it is. I'm going to define θ2 from the log gradient at the point of inflection, and that's going to be 0.413. And the other two are, again, they're not particularly physical, they're functions of the other parameters in the simulator, and in reality, they're functions of reality, they take those particular values, 12.172 and 2.236. So there are my 4 parameters, 10, 0.413, 12.172, 2.236. Those are the things I'm interested in. Right. So what happens when we calibrate a model without putting in the model discrepancy? So calibration, or inverting models, is another term that people often talk about. Simple matter of linear regression through the origin in this case. Here are some results. Okay, now I've taken various sample sizes. I've taken observations over different ranges. So the range that I showed you the picture for was the 11 points in this range, it's 0.1 to 4. But I've also done a shorter range and one further out, and I've done 11, 31, 91 observations, and actually I know what happens if I have an infinite number of observations. And you'll see what happens here is that we get values of the parameter, estimates, with a standard deviation from this linear regression. Okay, eventually we become absolutely sure what the true value is, but in no case is it 0.65, which is the true value. Okay, so this is an important point here, that we're going to miss the true value. Fair enough, our estimates are only estimates, they're not going to equal the true value. But we are so sure about those estimates, we have a certain uncertainty around those estimates that never covers 0.65, certainly not when we get more and more observations. Here's a quick picture of what's happening here. I've taken away the 0.65 gradient, so this is actually the model discrepancy is the black line. And you see what's happening with the short range, the first range from 0.1 to 2, I'm fitting a line through at that range. And then I fit a line over this range and then over the wider range. In all cases, what I'm doing is I'm fitting into the model discrepancy. And this is what will happen in all of your models. When you try and calibrate them or invert them or whatever you want to call it, Michael calls it history matching, whatever you do, your fitting will be fitting to the model, the reality, yes, but also to the model discrepancy. If we use the same thing on the hot and cold model, it's actually even worse. Here are the true values to remind you of them on this side here. And once again, we're nowhere near. Nowhere near. Okay, this is 91 observations in every case. And all the estimates are just the posterior distributions of all these parameters that just don't cover the true value. So the fourth consequence, calibrating without including model discrepancy produces biased estimates of all the parameters, including physical parameters. Well, obviously, there's no sense in which you have bias for tuning parameters, but biased estimates of all your physical parameters. And the more data you get, the more sure you are of these wrong values. The more convinced you are that you know the value and it's wrong. So what you should do when you do this, if you don't include model discrepancy, is simply say, I've done this calibration and I know it's wrong. I just don't know how wrong it is, which is just as bad as not having uncertainty in your predictions in the first place. All those three objectives I talked about, scientific progress, interpolation, extrapolation, they will all fail. None of them will work. You will always, if you get enough data, have a prediction that is with an uncertainty that's far too tight and that doesn't cover the truth. So let's try now putting the model discrepancy in. This is the general statement. Calibrating, inverting, tuning, matching, whatever you call it, a wrong model gives parameter estimates that are wrong, not equal to their true physical values, they're biased, and with more data we increasingly believe these wrong values. These two models we've just shown are trivial, of course they are, but all models have the same feature. They're all wrong. The more complex the model is, the harder it is to see just how wrong you're going. Even with that simple machine, you actually need quite a lot of data with rather tight error bounds to see that the curvature is happening in there. So what we can do about it is start putting the model discrepancy in. So this was the paper I wrote with Mark Kennedy in 2001, widely cited, introduced the idea of this model discrepancy, and we modeled it as a zero mean Gaussian process. And we naively thought at that time that this was the answer to the problem. It acknowledges additional uncertainty and mitigates against the overfitting of theta. We thought that this was going to be the panacea, so that you would get everything right. You'd be able to do all those three things: scientific progress, interpolation, extrapolation. So we add this model discrepancy term into the linear model of the simple machine. We've now got z is beta x plus delta brackets x plus epsilon. Delta is modeled as a zero mean Gaussian process. And the posterior distribution of beta is now going to behave quite differently. The results I'm going to quote you here from the study that was done with Jenny Brynjarsdottir and is published there. And it's published in Inverse Problems. I never thought I would publish in a journal called Inverse Problems because it's all about mathematics in there. I don't do much mathematics. But we did, and they accepted it, and were actually very pleased with it, apparently. So here's some pictures. First of all, if you don't have the model discrepancy, this is what I was showing you before. This is all for the observations in the middle range, 0.1 to 4. So the estimate is around here, and the uncertainty gets narrower and narrower as you have more and more observations, till you become totally convinced that the true value is there, whereas in fact it's here. If you use that Gaussian process prior distribution, you do a bit better, but you still don't get it that good. And the reason is your posterior distribution is never going to converge to a point. There's always going to be posterior uncertainty about the parameter. Here it's converging to a point which doesn't completely exclude the true value, but it's still in the wrong area. So we haven't solved the problem completely there. When it comes to an interpolation, we do get that right. So here's a point 1.5, it's well within that range, 0.1 to 4. Without the model discrepancy, you get it wrong, and as the sample size goes up, you'll get it same wrong, but more and more sure. With the model discrepancy, and even with that simple Gaussian process zero mean model discrepancy, you will learn the true value at 1.5 or at any other point between 0.1 and 4 as you get more and more observations. Prediction within the range of the data is possible. It does get better with more data, and you will get it right. But when it comes to extrapolation, again, it doesn't work. Without model discrepancy, it clearly gets it completely wrong. With the model discrepancy, again, you've got uncertainty, and this isn't too bad. the true value is within our range. But actually, if we started trying to predict further out for larger x, it would get a whole lot worse, and we would end up with predictions that are completely wrong. So we haven't solved the problem. Interpolation is fixed. Scientific progress is better, because at least you don't kid yourself that you know the true value exactly when you've got lots of data, but it isn't necessarily still going to cover the true value properly. So that's not fixed. And extrapolation likewise. We get wider prediction intervals, which may help, but they may still not be wide enough. Typically won't if you're extrapolating far enough out. So that's not fixed either. So what's going wrong? The problem is that the formulation with model discrepancy is not identifiable in statistical terms. For any theta, there is a delta that will enable you to match reality perfectly. The problem is that delta is a function, it's not just a number. So my reality is eta plus delta. So given any value of the parameters, a given reality, the model discrepancy is defined to match that reality perfectly. That's the model discrepancy function, if that's the value of theta. Suppose we have an unlimited number of observations, we can learn what reality is. That's what we're observing with error. So we will learn what reality is, at least within the range of the data. So that's why interpolation works. But you still won't learn what theta is. Theta could be anything, you see. You know what this reality is, but because you don't know theta or delta, you could pick any value of theta and there would be a delta to match it. You don't know what theta is. It could be absolutely anything. And there'll be a model discrepancy to go with it that will perfectly represent the observations you've got. And we still don't know what reality is outside the range of our data, so we won't be able to extrapolate either, particularly because we can't learn the values of the physical parameters which are there to help us predict reality in the extrapolation situation. So this is the crux of the problem. And this is the problem that naively I didn't realize at the time we published that paper, even though it was mentioned in the discussion by one of the discussants. I was so convinced I got the answer, as some of us are sometimes, aren't we? We tend to be a little bit arrogant. Oh, I'm just speaking personally. I mean, I don't know about you guys, but I certainly tend to be a little bit arrogant at times. So yeah, we thought we'd got the answer and didn't even pay attention when somebody pointed it out. It took a little while, not very long, before we realized that actually there was this problem there. So that's what the paper with Jenny Brynjarsdottir was about, was to say, well, what can we do to solve that? And broadly, it's about getting information. Calibration, in a formal sense, gives you a posterior distribution, a joint posterior distribution for theta and delta. Actually, it also, because you can't run the model all the places you'd like to, eta is included in there as well to some extent. We'll ignore that for the moment. Certainly in the examples we've been using, we don't have any code uncertainty. But certainly, you get a joint posterior distribution for theta and for delta. Non-identifiability means that there are many equally good fits to the data. There's a whole manifold through that space of theta and delta where the likelihood from the data is constant. The data are telling you only how close you are to that manifold. The best estimate is somewhere on that. Get a little bit further off, you know how depends how much good data you've got before that likelihood falls way off. So that the data are only telling you that much. Within this set, the prior distribution counts. You can get more and more and more and more data, so you identify that whole track of possible theta and delta values as closely as you like, but the data only tell you you're on that track, you're on that manifold somewhere. Within it, what matters now is the prior distributions. If you put prior distributions on theta and delta, they will pick out a most likely point on there. They will pick out how much the uncertainty is along that manifold. But it's only the prior information that's giving that. And you're not going to get any more prior information from the data by definition. So that's why you will never know for sure, and why you will only have any good ideas about it if you've got appropriate and sensible prior distributions to begin with. So to learn about the physical parameters, to learn about theta in the presence of model discrepancy, we need better prior information. So let's think about some better prior information. In that simple machine model, I know that delta is going to be 0 at the origin. And indeed, I know that its gradient is 0 at the origin. Because at the origin, I've got my model says that's beta is that gradient. But then it's going to fall off. It's going to become increasingly negative as I move away from the origin. So I've got that information. That comes from my understanding of the problem, of the context, the physics, and also what I put in the model and what I haven't put in the model. And the key to writing down prior information about the model is for the modelers to understand what it is that's not in the model. Have some sense of how this model is going to fail because of not putting things in. I often say the best way to find out about model discrepancy is to go and ask a modeler what they would do with their model if they had another £1 million to improve the model. They always know what the next grant would be if they could do it. So they know what they would put in. They know how they would change the model. So how would that translate into differences in the outputs? And again, they usually know this because there's some sense in which, well, I need to put that in because my outputs won't do this correctly if I don't. So that information, at least some of it, is there. It needs expert knowledge elicitation. It needs to be drawn out from the experts in order to give you some idea about it. In this particular case, the minimum we can say is this much, that delta is a function that's going to do this. Sorry, from your perspective, it's going to do that. Okay? Starts at 0, gradient 0 at the origin, and then it starts falling off. So let's do that. So we conditioned the Gaussian process, and it's rather hard. It certainly was hard then. I think there are better tricks now, but hard to condition it on being the gradient being constantly negative. But we did anyway do this. So the information we put in is it's 0 at the origin, 0 gradient at the origin, and the gradient is negative at a couple of other points. And we get better answers. So with that constrained Gaussian process, here's the posterior distribution for the beta parameter. And it now does properly cover this 0.65. It's never going to get close, it's never going to collapse to 0 uncertainty. So with lots of data, we are at least in the right ballpark. It's not bad. For it to have been really good would have to be that somehow reality, the true model discrepancy is exactly like we predicted it to be. And a Gaussian process doesn't do that. I mean, I've constrained it to be negative gradient at 2 points. That's not constraining it to the gradient to be negative everywhere. So I've got a certain amount out here. You'd have to work harder, put more information in to get better than that. And what you know always is that whatever you've put in isn't enough. Isn't enough for you to be sure that you've got the true physical values out there. We have improved learning about beta. We would need to constrain delta at higher x values for improved extrapolation. We would need to be forcing that gradient down to be negative all the way out to where we want to predict. So that prediction at 6, at x equals 6, will still be bad. So putting prior information in about the parameters, putting prior information in about theta obviously helps, but to some extent you want the data to be telling you about theta. It's theta that is what you really wanted to learn about. So very often that prior information needs to be weaker than the data is going to give you in some sense. So thinking about the model discrepancy is the crucial thing here. Putting more information in about the model discrepancy. The better that is, the better your answers will be in terms of learning about parameters, being able to use the model constructively. It's not so important if all you want to do is interpolate. Even then, I said with interpolation you will get it perfectly if you've got enough data. Well, typically we can't get enough data. Even then, therefore, it's useful to get the prior information right, so that then you will get a better answer even for your interpolation. But you have no hope when it comes to learning about true physical parameters or extrapolating if you don't put in meaningful prior information. And all the people that think they can do this without Bayesian methods are completely deluded. All right? Because clearly the prior information is the only thing that will give you the answer here. So the fifth consequence, incorporating even a crude model discrepancy term enables interpolation with a decent amount of data. But learning about physical parameters and extrapolation are intrinsically insoluble unless you knew the answer to begin with, unless you had the perfect prior information. Nevertheless, realistic prior information about the discrepancy and about the parameters does help. So, on that rather depressing note, and with plenty of time left, thanks for getting up early enough. Thanks for your attention and questions.
Thank you for this very interesting lecture. Though I feel that I'm a little bit, put on, as we say it in Dutch, on the wrong leg. Because what you see as model discrepancy is actually, in my opinion, ignoring the friction term. Because you started already with stating that beta was the gradient in the origin. So then, by definition, it's wrong to use observations out of the range to predict the beta at the origin. So my strong opinion is that physicists that model should know what kind of physical reality they try to model.
Exactly, absolutely. So that's why, okay, I started with this crazy simple example, which nobody would really use, and of course as soon as we start thinking about that model discrepancy, we know what it should look like because we know that's what we didn't put in the model. So that's why I say when you want to learn about the model discrepancy, you ask the modelers what's not in the model. What would you like to put in next? Okay, and what is the consequence of it not being there? So in this case, there was nothing useful in the model. Okay, we knew what was missing, so we could put that prior information in. But if in a real model, which already has a lot of science in it, a lot of complication stuff, we know that there are still things that are lacking. And it's that we can do. We can sometimes get a handle on some other things like the computation accuracies, the solution errors and things like that. But what we can't get this clear information about without asking the right questions, and even then only partially get it, is what's wrong with the model. And all models are wrong.
Just as does it make sense? You probably are confident that your model is not horrible. So would it make sense to fit without the model discrepancy and get biased parameters and then use them to inform your prior on the parameters?
I don't know, because you're going to get from that an estimate of the parameters which you know to be wrong. You don't even know which way it's wrong and how wrong it is. So you may have some sense of what sort of amount of error could be in your model. How does that translate into error in your parameter? I I mean, I don't know. What would you do?
Just, in the face of having to do something and not wanting to slap an uninformative prior on it, I just wonder if there's any value in taking an approach like that. You're not facing any sort of obvious inconsistencies.
I think you would still face the same problems that your answers are biased and you don't know how much, and without putting more real information in, you're not going to improve on that. But, well, try it. I mean, again, people may sometimes be able to say, okay, I know that delta shouldn't be bigger than this, and I have some prior belief about that. And maybe we can put that into the prior for delta in some sense. I haven't here. I've just allowed delta to be as big as the zeta or something was telling me. So that may help.
I think potentially the way we would address this is to use a biased estimate in order to inform our expert judgment about setting a more sensible prior on the parameters.
Okay. I'll hold fire on judgment about that. I think it's. I can't see how it would work, but
But you sort of know what we do. We're interested in natural frequencies and material properties, and we know they can't get bigger than this, and they can't be smaller than this. And so, together with a biased estimate, maybe we can actually come up with something a little bit more refined.
Okay. But that would be putting in knowledge and thinking at the same time. Okay, so it's not mechanistic.
No.
Oh, okay. Right.
There'd have to be some associated expert judgment.
Right. Okay. And very often when you're in the situation of asking about these things, and you're trying to formulate expert judgment about things, particularly when you're asking people who've already had some experience with the model, they have that kind of information already. And it's factored into what they're doing.
I don't think you could make it mechanistic, because you just end up with an uninformative prior again if you wanted something to apply in every case.
Mm-hmm.
I have a question. I wanted to bring a bit of a more optimistic view after the last concluding slide. My take here is that all those three things you want to do is in extrapolation and prediction. You may be able to do them when you want the relative.
When you
want the relative comparison. So you don't want to get really the absolute material parameters, but you only want to take clinical decisions. Clinical decisions where you know which patient is doing well, which patient is doing worse. And although your thresholds of decision are not absolute, you know who is better than other, and you can go well with that. So can I challenge your main assumption of, unless you get the true parameter models, you cannot do anything? And can I introduce a more optimistic view where you can still do something knowing that you are systematically biased, and then your relative values are still holding?
This could work. I mean, I hadn't thought about that particular uses of models. There are many uses of models. I was taking, in some sense, the most generic ones. If you're using a model, very often models are anyway thought pieces in a sense. They're helping you to think through the consequences of certain things. You're not actually using them to make any definite decisions. And all of this doesn't matter then. The model is there simply to guide your thinking. If it's there to help you to make decisions, and those decisions only rest on whether the output is in some range, then again, that may be perfectly adequate. Or if it only rests on whether with these inputs I get a bigger value than I do with those inputs, then assuming that you can make some feeling about how big the model discrepancy could be, then this patient having a higher value than that one is okay, as long as that difference is big enough relative to what you know or believe the model discrepancy to be. But you've got to have that information in as well.
Chris, I'm trying to get my head around the advantage of this joint discrepancy. People appreciate, I'm not from the computer modeling field, this joint discrepancy and model fitting as opposed to a kind of more traditional statistical approach, which would be fit the model without the discrepancy, do careful model checking and validation and residual, and then fit a joint model with the discrepancy, and kind of learn about, you know, where there might be systematic biases or where there may be structural residuals, and learn, you know, which part of the parameter spaces are perhaps prone to the discrepancy.
Now that is perfectly valid. So typically, however you do this process, you're going to be able to come back with some sort of statement about, it looks like the model is wrong here in this kind of a way. And then you go back to the modelers, of course, at this point, and you say, is that because of something that's wrong in the model? Have I run it wrongly, or whatever? And if you've learned something from that, you can feed that back in, either by revising the model or by putting in what you've learned as prior information on the model discrepancy, because the data have suggested something that you then realize is a physical reality, and you can put that in as part of your prior model for the model discrepancy. That will help. But often these models are very big. You don't get that many runs, you don't get that many observations of reality, and it's all in a very big space. So conventional statistical models, well, you deal with big models as well, so you know the limitations of this.
It was pointed out that it's important to learn as much as possible about the model discrepancy, and so the example that, you know, sort of the gradient is zero, so that is sort of knowledge that can be systematically integrated. But quite often you make sort of assumptions that formally reflect prior knowledge that you quite often have related to stationarity and smoothness. And so is that not another source of uncertainty? And how do you about quantifying that, so the level of smoothness and the level of non-stationarity that you might then keep under the carpet by making sort of an implicit assumption that would have to be quantified as well?
I often get this sort of question when you think about building an emulator. You're making these sort of assumptions of stationarity and so on. And I often get that sort of question. But the point is that the model isn't stationary or non-stationary. The model is not stochastic. The model is a thing. Sorry, reality is a thing at any rate, but the model is a thing. So it isn't a statistical thing. We only describe it as with a probability distribution because it's representing my uncertainty. My uncertainty about it may be stationary in the sense that I have the same uncertainty about all points over the input space. If I don't, then I should be writing down that as part of my information that goes into the prior for the emulator. So that there are emulators that will incorporate that kind of information that says, I believe that there are jumps, there are changes, there are regions that have different kinds of behavior. So then you don't use the simple homogeneous Gaussian process as a prior. But that's not part of the knowledge I was talking about here. That's what you do when you're building an emulator.
Michael.
So as you were just saying, these things are meant to represent your uncertainty, yeah? So I'm trying to understand your representation of model discrepancy, yeah? Because it would seem to me that, firstly, that delta is a function of theta as well as x. If I tell you different values of theta were the case, sometimes I think the model will be pretty good, sometimes I think it will be pretty bad. The cove, yeah, I mean, you could easily imagine that for some thetas the model does nothing, and that would be what would happen. For other values, it would do stuff, and that stuff is badly described. So I think that the delta is certainly should be a function of theta, usually. And secondly, the correlation structure between delta of x theta and what the model output value is actually a complicated thing, which you have to capture. I mean, in fact, most of the modelers will say that automatically. They'll say the error is about 10%. They're actually building in a correlation in the discrepancy right there. Yep. So I think the more you get the discrepancy to represent your actual beliefs, then if it's complicated to analyze, if it's confounded and everything, well, that's just how it is. Your problems come when it wasn't what you thought, so therefore the analysis isn't what you think. But as long as you put it all in, and if it's all complicated, that is the answer.
I will dispute with you on part of that as to whether delta is a function of theta, and the way I think of it, it's not. But it is certainly true that you can have beliefs that say the model discrepancy, say, as you say, of the order of 10% or something like that. Or you may very well say that when the output is high, the model discrepancy can't go much higher because, you know, of physical constraints there. So I'm aware of that in an example I'm really working with. So that's real. So yes, you have to put that kind of information in. So again, model discrepancy independent of is not always the right thing either.
Why don't you think that delta should be a function of theta?
Because reality isn't a function of theta.
Yeah, but
Reality is just a function of the control variable.
Real. This is your view as to how different the model output would be from reality. So you're creating a likelihood function, and in that likelihood function you're thinking, supposing theta was this, what would my beliefs be? Supposing theta was that, what would my beliefs be?
But that's not saying that delta's a function of theta. It's saying it's correlated with theta.
Yeah.
That's different.
No, but your beliefs about delta, I mean, are...
My beliefs about delta are correlated with those about theta, but they don't necessarily. They're not a function of theta.
But delta's... Yeah.
Delta's not a function of theta.
Well, delta's a random function of theta.
No. You're making it too complicated, Michael. It's not necessary.
I heard this argument before. Let's have a couple more questions. Wolfgang, let's come and set up. And did you have Gary?
Well, mine was slightly similar, actually. So if I had like an ODE system with an internal state, does it make sense then for the discrepancy to be a function of that state? Which is kind of a bit like 10%, but that's
If I knew what you meant by a state in an ODE system, that would be helpful.
There's a DDT on.
Right. Well, maybe. Well, we'll get back to that same discussion, I think. Peter, one more question?
So, some authors have suggested one way around the identifiability problem is to put some constraint on the discrepancy, so they make it orthogonal to the model or some similar thing. Do you want to comment on?
Yeah. People have tried to define these things. The sense in which I can relate to what you're saying particularly is, to some extent, the same is all true in statistical models. That in a statistical model, you're assuming probability distributions for things, and those might not be the true probability distributions. And even with your, multi-model uncertainty type things, you don't necessarily cover these things properly. So, I've also given talks to statisticians saying, how can you even believe you can estimate the parameters in statistical models when you know your model is wrong? And I've seen people then define the parameter to be whatever the maximum likelihood estimate would give on these things, which is similar to what you're saying. So you define the thing, so it defines away the problem, but it gives you an answer that has no meaning anymore. It's an artifact. It's a sort of some kind of construction that actually no longer relates to what you can actually have a belief about. It's like, how does anybody have any beliefs about the coefficient of x to the fourth in a polynomial regression? It's crazy.
Okay, I think we can keep going all day this, but I think we should thank Tony. Yeah.
Thank you.
Hopefully this